So in this video, I'm going to look at how we work out proton environments for molecules. This will be exactly the same for carbons as it would be for hydrogens. So we're going to start with ethane. And if we look at the molecule just here, the first thing to recognise is that there is actually a line of symmetry. When you're looking for these environments, always check to see if there is any symmetry in the molecule, because things that are mirror images either side of that line of symmetry will be identical to each other. Now, either side of this line of symmetry, what we have is we have a CH3. Now, these CH3 hydrogens will all be identical to each other because they are hydrogens attached to the same carbon. So chemically they're identical. And if we think about the shape that we would see around a carbon, we would actually get this tetrahedral arrangement. So these three hydrogens are not at right angles to each other. They're actually in this tripod tetrahedral shape. And they spin. We've got this free rotation around any single bond. So these hydrogens here will be spinning around on that carbon like an axis, and so at any one point those hydrogens are identical to each other. Now, because we've got a line of symmetry, the hydrogens on the other side of the molecule will also be identical to the others. So we would have 6 hydrogens that are all absolutely identical, which means that on an NMR graph we would have one spike, and that would be it. Now, if we look at butanone next, butanone, if we look, there is no line of symmetry, okay? No line of symmetry in any way. Just looking at the diagram like this, hopefully you can see that. So we now need to start looking at the hydrogens. Now, first of all, if we look at the hydrogens that I'm going to colour in yellow, they're part of a CH2 group. Now, there are no other CH2s in the molecule. So these hydrogens have to be one environment. So we've got this CH2 group, the H's are one environment. We've then got 2 CH3 groups. But because we don't have a line of symmetry, these 2 CH3 groups will be different to each other. So we'd get one peak on the graph for the CH3s on the left-hand side. But because this is a CH3 group that is next to a CH2 group, whereas the CH3 group on the other end is a CH3 group that is, keep using them on colour, a CH3 group that is next to a carbonyl, chemically these are different groups. Okay, they are having a different sort of chemical experience. There'll be a difference in sort of the density of the electron cloud in different places. So we'll have an unequal distribution of the electron cloud because of the difference in electronegativity of the atoms and other things like that. So in this one, we would have 3 peaks because we have 3 different chemical environments. And the 3 peaks would be for the CH3 in green, the CH2 in yellow, and the CH3 that I've put in blue. If we were to look at butanal, again, there is no line of symmetry. And what we can see is just, first of all, look for any hydrogens that are on their own. And we can see that we've got a hydrogen that is on its own attached to the aldehyde group. Now, because there are no other single hydrogens attached to a carbon, that has to be one peak on its own. If we move along the molecule, the next set of atoms we get to is a CH2 group. Now, the CH2 group is next to another CH2 group. We have a CH2 group here and a CH2 group here. However, they are not the same. The CH2 hydrogens that I'm going to colour in green, they are next to the aldehyde group. The CH2s that I'm going to colour in blue are not next to an aldehyde group. Therefore, they must be chemically different. They are next to different things. Now, finally, what we can see is that we have a CH3 group. There are no other CH3s, so we can see that we've got a chemical environment here where there's no other hydrogens that are having the same chemical experience, if you like. It's a way of putting it like that. So in this molecule, we would have 4 peaks if we were looking at a mass spectrum of this.